Hi all, welcome to GradStats 2024 Lab Series. For our lab on logistic regression, I'm doing something a little different. I'm borrowing from recordings that I did last year, and it has the lecture, and then the SPSS Lab, and then the RStudio Lab, and the JASP Lab all in together, and that's why it's so long. But the timestamps, I'll put them in the description. But the SPSS Lab starts at 17 minutes. The RStudio Lab starts at 35 and 25 seconds. And the JASP Lab starts at 1 hour, 12 minutes, and 4 seconds. So feel free to watch as much of it as you want and enjoy. Hi class, this is Dr. Shantz and welcome to your video for logistic regression. In this video we are going to talk about what is logistic regression, conducting a logistic regression including evaluating the model and interpreting regression coefficients, and what needs to be included in reporting of a logistic regression. And that's before we jump into the labs for SPSS and RStudio. I did put some resources for you in the notes of the PowerPoint. So Plant SPSS Survival Guide, Chapter 14 is the one that goes over logistic regression, but also some YouTubes on running a logistic regression in SPSS and in R, and different articles or websites that might help wrap your head around this. So let's get started. So what is logistic regression? Well, it's used when the outcome variable is categorical. And there are two types of regression that are binary logistic, when the outcome only has two levels. That would be like, should we hire or not? Or is this going to be someone who recovers from surgery or not? Those types of yes or no types of outcomes. And multinomial logistic, which is when the dependent variable has more than two levels. And a logistic regression evaluates how well a set of predictors explains the categorical dependent variable. And we do this by looking at goodness of fit. You'll see that term used sometimes. So we're going to learn some new skills here. We're going to evaluate goodness of fit with the chi-square test. We're going to use a different type of model effect size. This one's called pseudo R-squared. And we're going to interpret contributions of the predictors using odds ratios. So let's see what this looks like. Logistic regression can be like, hey, the outcome is yes or no? Got that, no problem. But then it's a little different, right? Because we're not talking about a regression line that's from ordinary least squares anymore. We're talking about a logarithmic function, which is no longer a straight line. Logistic regression does have similarities with linear regression in that the model results indicate the impact or effect of the overall model. And the regression coefficients, they explain those unique contributions of each predictor controlling for the other variables in the model. But there's a lot of differences too. Logistic regression is not modeling a linear relationship, it's modeling a logarithmic relationship. And that pseudo R-squared, it's an effect size indicator, but not about how much variation is explained. It's a different type of effect size that we're working with there. We also look at the model in terms of how accurate it is, how accurate the prediction is according to the predictions of what they got right compared to all the predictions. And we'll go into that some more. And then different as well is how we interpret the regression coefficients and the predictors. We use the odds ratio to explain how much more or less a likelihood of an outcome per predictor would be. And we'll go into that a little more detail here. Let's start with a question. So what if we have a research question such as, what factors would predict someone reporting that they have sleep problems? Maybe it could be demographically related, like depending on how old someone is or gender. Or maybe someone who already has other symptoms, like not being able to get to sleep or not being able to stay asleep, would indicate they're more likely to report having a sleep problem. Or depending on how many hours a night they sleep would be an indicator. And when we have this dichotomous outcome of reporting sleeping problems, 0 being no and 1 being yes, and all of these categorical and continuous predictors, we have exactly what we need for a binary logistic regression. Now, to conduct the regression, we need to prepare the data, do our preliminary tasks like describing the data set and the study variables, assumption checks, but then we get to that model testing part where we need to evaluate the model and interpret the regression coefficients, and then write it all up to make it approachable and make the information available to our reader. So what does this evaluating the model look like? Well, this is output from SPSS, and the test that tells us about the significance of the model is the chi-square test. So similar to your F-test in linear regression, but the chi-square is testing if there are significant differences between the null model and the complete model. Now, what does that mean? Well, the null model is a model with no predictors. Now think about it. When we have our linear regression equation, we would have the outcome and then the y-intercept and the regression coefficients for each of the predictors, right? So what if we had no predictors? What would be left? Just the y-intercept. So the null model is just the outcome and the intercept. So what we're saying is, once we put in predictors, was there a significant difference between what was predictable with a null model and what was predictable with a complete model that has predictors in it? Because if there was no difference between having no predictors or having these predictors, then those predictors weren't worth it, right? So the first thing we look at is this chi-square test. We have our estimate of the chi-square, the degrees of freedom, and the significance value. Now, we also have the pseudo R-square in the model summary. And the two that we have here are the Cox and Snell R-squared and the Nagelkerke R-squared. And these, like I said, are ways that we can evaluate the model, but they're not exactly the same as the R-square we're used to that would explain percent of variance explained. Here, we can take the R-squared of this complete model and compare it to the R-squared of the null model to see that we have some improvement. Now, in the chi-square itself is sufficient to test for model improvement, but as you go into more advanced techniques where you're model building, you're actually looking at more or less deviance for each improved model. And again, as you put a predictor in, it needs to prove its worth for being there, for actually contributing to the model. Okay, another way we evaluate the model is with the accuracy of the model. This is saying, how well did this logistic regression get it right? And we can look at that by looking at true positives, true negatives, and the false positives and negatives. A true positive is when we predicted that the case would indicate a sleeping problem, and we observed the data was that they reported a sleeping problem. So yes, yes is a true positive. Similarly, if we predicted that this case would not report a sleeping problem and they didn't, then that is an accurate prediction, right? So those are times, true positives and true negatives, when the regression equation got it right. What it didn't get right was when we predicted that this case would report a sleeping problem, but they didn't report one. Or we predicted that the case would not report a sleeping problem, but they did. So these are in times where the regression equation did not get it right. And the way that we compute the accuracy of a model is you total up all of the positive and negative predictions and then divide it by all of the possible predictions there were. Multiply by 100 to get yourself a percent, and then you get the full percent of accuracy of the model. This particular model was accurate 75.1% of the time. So now on to looking at the specific predictors. And to do this, we use odds ratios. But let's look at our table here. Again, this one's out of SPSS. We have our basic regression coefficient estimate and the standard error. We know the significance level of these predictors, and we can see that 3 of the predictors were significant and the others were not. Also notice that, at least in SPSS, they put the constant at the bottom. Not sure why. R doesn't do that, but there it is. And where we go for actually interpreting these regression predictors is in the odds ratio box over here. This column EXPB is going to be the odds ratio for that predictor. And then we have our 95% confidence interval for the odds ratio. And odds ratios indicate how many more times or less likely the case would be a yes in the categorical outcome. For example, the predictor of trouble staying asleep, that third row, it has an odds ratio of 7.274. This means that those who report having problems staying asleep are 7.27 times more likely to report a sleeping problem. And because the range of the logic function is all real numbers, like 0 to infinity, you want to consider the value of 1 as your midpoint. Any predictor with an odds ratio of 1 means it's just as likely to be classified as yes as classified as no. In other words, it's like a 50-50 likelihood with no real significant effect. So notice that any confidence interval that has 1 within it, like 0.484 to 1.663, would have 1 in that range. Whenever you see that, also notice that that predictor is not significant. And then another thing going on here is this less than 1. If the odds ratio is less than 1, it means that that case is less likely to indicate a sleep problem. So more likely it would hit the 0, no reported sleeping problem, instead of yes, reported a sleeping problem. And we'll go into this a little more detail on the lab where we have all of the output. Once you have all your information, you're going to be ready to report the logistic regression. The model results would be the chi-square test. So the chi-square, the degrees of freedom, this n is going to be the n in the sample that is used in the regression. So it might be less than the actual sample size of the whole data set. So you want to watch for that. The estimate of the chi-square, the p-value, and the Nagelkerke, or whatever pseudo r-squared you want to report. we don't have to do the confidence interval for the pseudo R-squared. And then you're also going to report the overall accuracy of the model in terms of how often did it get it right. For the predictors, you're using the odds ratio to explain how many more or less times those cases would be in the outcome. So your interpretive sentences come into play there. And then your table of results is going to include most of the information that you got from your predictors table. So your regression coefficient, the standard error, the significance, and the odds ratio information. Now, logistic regression can be tricky. It might not be accurate if the sample size is too small. It can't handle having too few cases in any of the categorical levels. So it's got to have enough male, enough female. It's got to have enough people reporting a sleep problem and people not reporting a sleep problem, things like that. So you have to take a really good look in those preliminary tasks of seeing and those descriptives, looking at how many cases are in each level of the categorical variables that are being considered, which makes missing data really problematic. So when a logistic regression has like fatal errors, it just won't converge. It won't find its regression coefficient, and you'll get an error message or blank results. But, well, on that happy note, let's go try out the labs. This would be a good time to take a little break, get your lab materials together, and we will start with the SPSS Lab. So starting our Lab 6 in SPSS for logistic regression. And again, logistic regression is used when our outcome variable is categorical. And the two types of regression are binary logistic and multinomial logistic. And it just is determined by how many levels are in the outcome variable. The one we'll be using in this lab is binary logistic. And a logistic regression evaluates those predictors, variables for explaining the likelihood of a level of the categorical dependent variable happening. For example, what are the risk factors for someone recovering from an addiction or using a type of therapy? Or what is the likelihood that this person should be hired? So those are very real questions that we ask in applied settings, and you'll see logistic regression used a lot in different applied and research writings. So what you'll need for the SPSS Lab is the data set called sleepLogistic.sav and the Labsheet Lab6 Logistic. Grab those things and we will get this started. So logistic regression is going to be used when we have an outcome that is categorical. And for our lab here, we're running the binary logistic because our outcome has two potential values. One being no, that someone did not report problems with sleeping, and yes, someone did report problems with sleeping. We are using the sleep.sav file from Palant, so from your SPSS Survival Guide book, and we are looking at what factors predict the likelihood of someone reporting sleep problems. For different goals and new skills we are learning in this lab is an introduction to binary logistic regression, evaluating the goodness of fit of a model using chi-square test, and also identifying information in the output to be able to report about the model results, and being able to interpret how each predictor contributes to the outcome variable using odds ratios. And in the end, creating a table for organizing your results so that you can communicate this back to your reader. So go ahead and open up your sleep.sav. And this is a real data file of a survey conducted with university and staff to identify sleep-related problems. The variables of interest we want to take a look at are the outcome, which is categorical. Did someone report problems sleeping at night? No or yes. And notice that you always want the no to be coded as 0. So if something is absent, it's coded 0. If something is present, you code it as yes. And that's part of that setting up the data to get it ready for analysis. But we also have a gender variable called sex. 0 is female, 1 is male, an age continuous predictor, and then a hours of night slept on weeknights, which is going to be a continuous predictor, and then 2 more categorical predictors if someone reported having problems getting to sleep and if someone reported problems staying asleep. So opening up your sleep.sav, you want to first start with your preliminary tasks. And we're not going to do preliminary tasks in the lab because I don't want us to move on with time. You already know how to describe the data set and describe the variables of interest, reporting your frequencies for your categorical variables and your descriptives as far as mean and standard deviation for your continuous variables. And assumption checks that you want to do for the logistic regression are going to be looking at normal distribution of any continuous predictor variables and looking for if there's any multicollinearity, anything highly correlated between your continuous predictors. And we only have 2 continuous predictors here, the hours of sleep per night and age. So you run a correlation to find out if they are highly correlated. What's too high for multicollinearity purposes? 0.9 is too high. And then we move on to actual model testing of the logistic regression. So we're going to go to Analyze, and then to Regression and Binary Logistic. We have our dialog box. We want to come down to our outcome variable of when someone reports having a sleeping problem. And then for our covariates, or for the variables, our predictors here, we want the gender and age variables, and we want the symptoms, the other symptoms of sleeping issues, staying to sleep and getting to sleep, and we want the hours of sleep per weeknight. So our 5 variables there that are going to be our predictors. Next, you want to go to the categorical submenu here. Any variables that are categorical, you want to move them over to this categorical covariance box. And for all of them, we need to come down into this change contrast area and change it to first. So all of them should have the word first beside them. We'll hit continue here. And then we need to go into the options submenu. Here we want the confidence interval for exponent B. And this is going to give us the odds ratio values for those predictors. You can hit continue here. All right, we can paste, which gets us the syntax window, and run this. All right, let's take a look at what we have here. We have that 241 cases were in the analysis. That's because some of them were missing data. And that's something you'll need to know when you're doing your write-up later, that our N, our sample size for the regression, was 241. We also have information that the outcome variable, so reporting problems with sleep, no was 0 and yes was 1. That's a good confirmation that we have it correct. And then same for our categorical variables that are going into the regression. No is coded 0 and yes is coded 1. And then in our gender variable, female is 0, male is 1. Again, those are going to help when you are trying to interpret what does the regression tell us here. This block 0, we don't use it a lot, but it is information. This is when there is no predictors in the model. So variables not in an equation, all of our predictors. Why is that? Because this is the null model. This is the baseline model with no predictors, so that we can compare our enhanced or more complete model to the baseline to determine if it's a better fit to the data than having no predictors. If we added a predictor and it wasn't even different than adding nothing, then we know that predictor wasn't worth anything to have in the equation. But then we're going to move down to this part called block 1. And this is where we get the information we need for the write-up. We have the chi-square test that the chi-square came in as significant, and it's at a value of 76.02 with 5 degrees of freedom. And you'll need all of that for the write-up. We also have the information about the pseudo R-squared, both the Cox and Snell and the Nagelkerke. And typically I've seen the Nagelkerke used. So you're going to report the pseudo R-squared, but we don't need to get the confidence interval for it. Another thing we use to determine the goodness of fit or the quality of that logistic regression is going to be in how accurate it was. And you see this on the classification table. How often the logistic regression reported or predicted that it would be yes that someone reported sleeping problems compared to what they actually did. So here you have your true positives at 71. So we were predicted yes, and yes was the actual data. And we have our true negatives. Our true negatives. We predicted that these cases would not report sleeping problems, and that was the case in the actual data. Those would be when the logistic regression got it right. The other two, when we reported yes, that we predicted that these 28 cases would indicate having a sleeping problem, but actually they did not. That's when the logistic regression got it wrong. Same here for the 32. The regression predicted 32 cases that would not report a sleeping problem, but they actually did in the data. And that's, again, where the logistic regression got it wrong. Overall, the regression was 75.1% accurate in predicting the correct thing. Then we go down to information about the predictors. We find that in the variables in the equation table. And the significance column is what tells us which predictors were contributing to determining if someone was going to be in the no problems reported or the yes problems reported categories. So our predictors of getting to sleep, staying asleep, hours of sleep per weeknight, and the age and gender are all on here. But notice that the only ones that are significant are the problems staying asleep, problems falling asleep, and the hours of sleep per night. So we have the estimate. This is the odds log, the standard error, and then the walled test is kind of like a t-test that we would have in this same type of table in linear regression. The degrees of freedom, the significance value for each of those predictors, And then this last three columns are the odds ratios themselves. We have the odds ratio and the 95% confidence interval for the odds ratios. So let's take a look at those in more detail. For someone who reports that they have problems staying asleep, they were 7.27 times more likely to report having problems with sleep. Next row, those who reported problems falling asleep were 2.05 times more likely to report having problems with sleep. And here, the hours of sleep per weeknight, that one's an interesting row, because for one, the odds ratio is less than 1. And that means that that one value is like the midpoint. Something with a value of 1 for the odds ratio is kind of right in the middle, that they could just as likely report a sleeping problem or not report a sleeping problem, right? But when it's less than 1, it's almost like that, that negative relationship that would be with correlation. As one goes up, the other one goes down. It's more like that, where you have less than 1 means that the more hours of sleep someone gets per night, for each 1 unit increase in hours of sleep per night, you would have a 0.64 times, so less than 1 in 1 times likelihood of reporting a sleep problem. So more hours of sleep per night means less likelihood that they would report problems sleeping. How much less likely? 0.64 times. So really different there, because it's a continuous variable. It's a continuous predictor. So that's when we get back to that for every 1 unit change. For every 1 hour more on average slept per night is this much less likely that someone is going to report a sleeping problem. So that one's a bit of a more challenge there. Like I said, this continuous predictor gets a little hairier. Having a less than 1 odds ratio means it's less likely the respondent would report a sleeping problem for every 1 hour more of sleep, because it's continuous. Whereas our categorical ones, we just look at it as those who do report a problem in this area, like falling asleep or staying asleep, would be that many times greater of indicating problems sleeping. And it's greater because it's over the value of 1. Okay? All right. So that's the tricky part there. The last thing you have on this is your example write-up, where you let the reader know what type of regression you run, what was the analysis, what variables were involved, and what the test statistics were. You also can indicate what kind of impact or what kind of effectiveness this model shows. Like, yes, we know it's significant with the effect size of Nagelkerke, but you also let the reader know, how good is this model? Well, this model will correctly classify 75.1% of the time. That's how good it is. Then you go into your regression coefficients and you have to explain it in terms of odds ratios and how many times more or less likely someone indicating or someone in that predictor would also fall into the yes category of the outcome. Yes, this is someone more likely to report problems with sleep. We did find that age and gender were not significant predictors of reporting a sleep problem at all. And then your table for presenting this type of information to your reader would look something like this. Just making sure you let the reader know which predictors were significant and what the odds ratios were and the confidence interval for the odds ratios. All right, that is it. Like I mentioned in our lecture, logistic regression is a more advanced technique. This is just a starter, and it can be a little quirky about missing values, small sample sizes, or not enough cases in each of the categorical levels. So definitely look into it more, follow up on some resources to get a little more information about logistic regression. So next we're going to do the same lab, logistic regression, but now in RStudio. Materials you will need for working in R are going to be a data set called sleepLogistic.dat, so tab delimited, and the Lab6 script. So grab those things and we'll get started. Hi class, welcome back. We are continuing our series on logistic regression, and in this part we're running a lab in R on Binary Logistic. Some of our skills here that we're working towards are the introduction to binary logistic regression, being able to evaluate the goodness of fit of a model using a chi-square test, identifying the information we need in the console for the write-up to be able to explain if our test is significantly improved, and also the accuracy of it given how well it predicts the outcome. Also, we want to be able to interpret the contribution of predictors using odds ratios and create a table for organizing the information for our reader. We're only using the tidyverse package, so I'll start by loading that. And then we're going to import the data set that is the sleep data from Palant, the SPSS survival guide. And all I did was export it as a DAT file, a tab delimited file, so that when we import into R, it keeps the names of the levels for those categorical variables. Anyway, we're going to set ID to character and set our factors up using the import wizard here. I'm going to name the dataset Lab6, and just letting you know that when you import factors or when you set up factors in the import wizard, the first one you list is going to be coded 0. So if you already know that you want no to be 0 and yes to be 1, or that you want female to be coded 0 and male to be coded 1, you can put it in that order when you're importing using the import wizard, and it should already be that way. Regardless, we'll have a way to relevel if we need to when we get into our preliminary and prep tasks. So let's first import this data set. I called it sleepLogistic.dat, and it is a tab delimited file, so I need to adjust that and let it have time to do the updates every time you make a change. I'm going to name it Lab6, and the ID set to character. Sex is going to be a factor, and because I know I want female coded as 0, I'm going to list it first. And then the other categorical variables are at the end of this. We have those who indicated having a problem with sleep, those who indicated that they have a problem staying asleep, and those who indicated having a problem getting to sleep. So each of these need to be turned into factors, and I want no coded 0, so I'm going to list it first in this dialog box. I have to let it update, and then I scroll back to the end again to get the next one. Now you can do this with code. You can do it with script. Just to make sure that the absence of reporting is coded no as 0, and the presence is coded yes as 1. Okay, so I have my factors in place, and all of the other variables of interest are continuous. So I have gender set and the other factors, and we're ready to roll. So I should have the 271 observations of 55 variables here. That's good. And the research question we're looking at here is what factors impact likelihood of reporting a sleeping problem. So our outcome that someone reported a sleeping problem, no is going to be 0 and 1 is going to be yes, and that's our dichotomous outcome variable. Our other variables are gender in the sex variable of 0 coded female and 1 coded male, age, which is continuous, hours, average hours of sleep on weeknights, which is continuous, and then reporting problems, being able to get to sleep, no reported problems, and yes reported problems. Or reported problems being able to stay asleep. Again, 0 is no and 1 is yes. Okay, so the first thing we're going to do is subset the data. We don't need 55 variables. We only need the ones that we're interested in. So I'm going to create a new item called Lab 6.1 and select out of Lab 6 just the variables of interest with the ID variable as well. So running that, I now have 271 observations of 7 variables. Let's take a look at that. Okay, so we got the ID, we got problem sleeping, that's the outcome variable, the gender, age, hours of sleep per night, and problems getting to sleep or problems staying asleep. Now notice all these NAs. That's going to be problematic for logistic regression. So it's good to take a look to see what's going on. I have 23 missing variables in age, 1 missing with hours of sleep per night. So I'll need to address that. Let's prepare the variables for analysis so that let's just make sure that 0 equals the absence of the thing and 1 equals the presence of it. And I'm going to look and see what we have right now, running the contrast that we would do with a categorical variable. Looking at this, we see that no is coded as 0 for problem sleeping. Female is coded 0 for the sex gender variable. No is coded 0 for problems getting to sleep. And no is coded to 0 for problems staying asleep. If any of those are not coded no, you'll need to relevel to get them right. And here's the releveling, just to make sure that no and female are in the first spot so that it's coded 0. Okay? Mine are all good, so I don't have to worry about it. Okay, and like I said, logistic regression will only be able to work with the cases that have no missing data. So there are better ways at working with missing data, typically multiple imputation, to estimate what the missing value would have been given the covariance of the whole matrix, but we're not going to get into that on this video. So instead, I'm going to just drop the cases that have missing values. So writing on to Lab 6.1, so I'm overwriting, then drop the NA observations. So remember, we have 271 when we imported. I'm going to run this, and now we have 241. So I had 30 cases represented there that were missing values. Okay, now we're ready for model testing. Our logistic model looks a lot like what we would do with a linear regression model. We're saying that the outcome is predicted by these predictors using this data, and then that's where it changes. Here, the function is GLM, General Linear Model, and we have to tell R which type of the general linear model we're using. We're telling R we're using family equal binomial. And we're going to give this a name in the environment. I named it L6 Mod 1 for Model 1. You can name it whatever you want, though. So now I have L6 Mod 1 list of 30 in my environment. So let's check out these results. Pull this up. We have what the call was, what we told R to do. So it just kind of echoes back, this is what you told me to do, and this is what I got when I did it. Here, deviance residuals. Deviance means how far different the model was from the real data. So it's an indicator of how off track the model is when it's saying how well does this model represent the data that we have here. And what you're looking for here is that it's kind of symmetrical, that the middle is close to 0 and that you have like the max is 2 and the min is -2. The third quartile is 0.8 and the first quartile is -0.7. So you're looking for kind of a symmetrical deviance and that the middle is pretty close to 0. But again, deviance is telling us how off the model is fitting the real data, and that's an indicator. Next, we have the coefficients, and we're going to go into actually interpreting these in a minute, but I wanted to just look at what we have in the console here. We have our regular estimate of the regression predictor, the standard error, the z-value, which is the walled test instead of a t-test, and then the significance column. And then down in here, we have null deviance and residual deviance. Notice that the null model, which had no predictors in it, had a deviance value of 329. And then this model with five predictors in it, that's why the degrees of freedom went from 240 to 235, is because we used up, each predictor used up a degree of freedom, and that's the reason why we have that difference there. But the residual deviance is 252.98, so less than the null deviance. So it's good that now our model with all of the predictors in it is less deviant from the real data, from the observed data. So our prediction model is less deviant with the predictors in it. And then you have this AIC indicator is also an indicator of the model fit, but we're not going into that this term. All right. The null deviance and the residual deviance are used to compute a chi-square test and the R-square. So that's going to be our next task here. We have the model in the environment right there, and we can use the deviance values out of the model, it's right in there, to be able to compute the chi-square, the degrees of freedom for the chi-square, and the significance level of the chi-square test. So running those three, and we're going to place 3 new values here in the environment. The chi-square estimate, the chi-square degrees of freedom, and the chi-square probability or significance level. And then this line of code, where I list them out with a semicolon between them, just prints them down in the console, down here. So what do we have? We have a significant chi-square test, because 5.66 to the negative 15 is less than 0.001. It's less than 0.05, which is our cutoff. And a significant chi-square here is telling us between those two deviances, right? That's how we ran it, was comparing between the null deviance and the model with all the predictors, the mod 1 deviance. And is there a significant difference in the deviance between those two models? The significant chi-square says yes, there is a significant difference between the deviance levels of those two models. So that's saying that our new model with the predictors in it is a good model. It's better than not having those predictors in. So that the way we would write up our chi-square stats line, this is kind of the general form for it. You tell your reader the chi-square, what test is being run, the chi-square. You tell your reader the degrees of freedom, which we have, our sample size in the regression. And remember, that's why we had to get rid of the cases that had missing values. So the amount of cases in the logistic regression was 241. Then the estimate of the chi-square, the p-value of the chi-square, which we would just say p less than 0.001, and the effect size, which we haven't gotten yet. So how do we get that effect size? Well, those deviance scores are also used to calculate the effect sizes called pseudo R-squared. There's one called Cox-Snell, Cox and Snell, and one called Nagelkerke. There we go. And so we're using R as like a big calculator here to calculate these. This is what we would use for calculating Cox and Snell pseudo R-squared. That we're making a new thing in the environment called RCS, and it's going to be informed by or assigned by 1 minus the exponent of this value. The mod 1 deviance minus the null deviance divided by the sample size in the model. Similarly, we need Cox-Snell to be able to get the Nagelkerke. So this would be a new thing in the environment called R.n, taking what we already just computed and then taking 1 minus, then the within the parentheses there. So two different ways of calculating pseudo R-squared, and we don't need to go through all the math theory on that, but that's why I leave you the information here so that you can use it. Now, if you do use these equations in future work, you're going to need to change the information to where it matches your model, like the name of your model and the sample size in your regression. So watch out for those. I'll go ahead and run these. And I have 2 new items here in the environment, including the pseudo R-squared of Nagelkerke. And that enables me to finish writing my my chi-squared model stats. Okay, another way that we communicate to the reader about how good is this model, like really, is explaining the accuracy of it. How much of the time did the model get it right? Did it identify when someone had reported a problem sleeping and when someone did not report a problem sleeping? And to do that, we're going to need a classification table. So we're going to run this guy and put it over here in the environment. What does this say? It says create a new item called class DF. And you can name it anything. I'm just giving it a name that makes sense to me. It's classification data frame. That's all. It's being assigned by the function data frame. So create a data frame called class DF, in which I have a variable called response. What is that variable value is going to be? It's going to be the actual data. So in the Dataset Lab 6.1, the variable called problem sleeping. So that's the actual observed if someone indicated they had a problem sleeping. And then comma, it's also going to have a variable called predicted. And that's going to be, I'm rounding just so that it's not so long, because logarithmic estimates are kind of got a lot of decimal places. So that's why I'm rounding it down to just a number. But the fitted, if you remember when we were working with model level assumptions and getting the fitted values, those are the predicted values. The model predicted what this was going to be. So fitted values is predicted of the model, right? So I took one variable out of the data set and another variable out of the model, and I'm putting them together to make a data frame called class DF. Okay, so that's there in the environment, and now we can make a crosstabs that is the predicted by response, and the data being used is that new data frame we just made. So when we do that, we have in our console here the classification table. Here's our response. That's the actual observed response. And on this side is the predicted. When we predicted no, we predicted that this case would say they had no problems with sleep. And the actual response being no was this column right here. The times that we predicted no and it actually was no is called a true negative. Similarly, the times that our model predicted yes, because yes is 1, predicted yes and the response was yes, was 71 times, and that is a true positive. The other two are false. This is a false negative. We predicted, not going to happen. They're not going to report a sleeping problem, and we were wrong. 28 here is a false positive. We predicted, yep, they're going to report a sleeping problem, but what really happened? No, they didn't. We take these values to compute the overall accuracy of the model. How do we do that? We need to add the true predictions, right? The true positive and the true negative. Every time the model got it right, add those together. And then out of all of the predictions, so out of the true positives and true negatives and false positives, false negatives, all of the potential total predictions is what would go in the denominator. And then we can multiply all that by 100 to get a percent. So we're basically using R as a big old calculator again. We run this, and we have 75.1% of the time the model was accurate. And that's another way that we communicate to the reader, how good is this model anyway? Well, it's 75.1% accurate. So now that we have gotten some information for reporting how good the model is, like what is the goodness of fit there, we're going to now go into talking about the predictors themselves. So to do this, let's go back to that summary of our model and see what we got here. Our model is showing with the column that's significance that 3 of them are significant contributors to identifying when someone was likely to report a sleep problem. They are if they reported problems getting to sleep, if they reported problems staying asleep, and how many hours they sleep per night, weeknight. So let's check out these, because what we need to be able to interpret and communicate the level of impact these significant predictors have is we need the odds ratio. And to get that, we raise that log odds to the exponent. So we're taking the exponent of those coefficients and also taking the exponent of their confidence intervals so that we can get the odd ratios and their 95% confidence interval. There's that and that. So the gender variable, see how it's so close to 1? That's why it's not significant. If a odds ratio is close to 1, then I'm 1 times as likely to report a sleeping problem. Well, 1 times is just like itself. So there's no way to classify. Like, it's not a significant way to say, oh, you're going to report a sleeping problem and you're not, if I'm pretty much 1 times as likely to do so. So anything close to a 1 on the odds ratio is not going to be a significant predictor, right? Notice how both age and gender were not significant. It's because they really are not contributing to know if there's going to be more likelihood or less likelihood of reporting a sleep problem. And remember, 1 is that central value there instead of 0, like with linear regression. But here on when someone reports that they have trouble getting to sleep, they are 2 times more likely to report a sleeping problem. And that was one of our significant predictors. If someone reports problems staying asleep, they're 7.3 times more likely to report a sleeping problem. So that's how we interpret that. You take the ones that are significant, and it's how much more likely times is the trick of it. Now, it's different if we're now under 1, because remember, 1's that kind of middle of the ground, 50-50, not really contributing to the equation, right? To the ability to classify. But if it's under 1, now it's less likely that they are going to report a sleeping problem. And remember, the hours per weeknight is a continuous variable. So now we have to interpret like we would interpret a continuous predictor in linear regression. For 1 unit increase, what's the unit? It's hours. So for 1 hour more sleep a night someone gets, they are 0.64 times likely to report a sleeping problem. Well, if I multiply by 0.64, I'm less likely. You see what I mean? It's almost like not a full 1, it's less likely. Anyway. Okay, with all of that and with our confidence intervals, right, we have the ability to write up, to make a nice little logistic table here. And we have that on the lab sheet where we report what type of regression was used, what was the analysis, and what were the variables involved in that analysis. And then give your reader the results, the test results, so the chi-square results, and also we want to let the reader know how accurate was this model. That's all part of evaluating the model level results. And then we go into explaining the variables that significantly contributed to the model, to classifying if someone was going to report a sleeping problem or not. And we do that by discussing the odds ratios and how they impacted the determination of someone reporting a sleeping problem or not. So that's your odds ratio and your interpretive sentence there. The weird one is when now we're less than 1. So you want to be careful with your wording there, that for every additional hour of sleep, the odds were 0.64 times lower that the respondents would report having a sleeping problem. And then, of course, age and gender. We're not significant predictors, so we don't even worry about putting that in the narrative about what the odds ratios were. The reader can always see the odds ratios for all of the variables in the table. And I think it's one of these, right? I think it's going to be SPSS. That's what it is. In SPSS, they don't give you the 95% confidence interval of the odds ratio for the constant. That's okay. You can just leave like a dash in that column for the constant or intercept. Alrighty. One last thing I wanted to show you in the R land here is I found a cool graph. I was looking for a way to graph the logistic curve of the model, and I did find one way, and I'll show you guys that here. What I'm doing is making a new item in the environment called predicted data. Again, you can call it anything you want, and it's being assigned by making a new data frame, and the variables in this data frame are going to be one called probability plot. Again, you can name it whatever you want. And what values go into that variable? It's going to be the model predicted values. And then I'm going to have another variable called prob sleep, which is going to be the actual observed data of prob sleep. So running that, I now have a new item in the environment with just those two variables I told it to have. Next, I'm going to order the data, and I'm going to order it ascending, so that decreasing is false means I'm going to go from the lowest to the highest, right? So I'm ordering this data set in a ascending fashion. And it's not going to show us anything. Like here, let's take a look. If I show, we got 8, 4, 3, 2, 7, 8, 7, 5, 8, 5. See how it's not in order? But then when I run this script here to put it in order, now I have all of these going from lowest to highest. See what I mean? So I put them in order first. And then I'm going to add a new variable called rank to the object called predicted data. And that new variable is going to be assigned by the number 1 to the last row. So kind of like case numbers, right? 1, 2, 3, 4, 5, 6, 7, 8, like that. But it's specific because we already ordered the data. So it's going from lowest to highest before putting on this rank number. So I'm going to run this. And now in the predicted data, we have a new variable called rank, and it just goes right up to 241. Okay, with those two in place, we're able to plot the predicted probabilities against, not heart disease, that's where I got the example from, of each sample reporting a sleep problem. And by color, by whether or not they actually had a sleep problem. They actually reported a sleep problem. There we go. So here, asking for a ggplot of that new data frame with those with rank and probability plot on the axes, and with these different labels and colors and shapes to make it pretty. So there's what my logistic function looks like for the data. Now, if you want to see how to make this graph, you can check it out on StatQuest, and that's why it said heart disease there, is because I got it from there. And here's the YouTube for it. They are talking more about machine learning, so some of it isn't going to make all as much sense for us. But if you watch it through, you can see how, or this script, grab this script and be able to change it to work with your own if you're trying to get a graph like this. I wasn't able to find a similar graph in SPSS, so if you find one, let me know. And like I said, this is just an intro into logistic binary regression here. And if you want to, or if you find you want to learn more about it, definitely look into those resources I put in the notes of the PowerPoint. And there you go. So we're going to run Lab6 Logistic Regression again, now in JASP. And we're looking at the same research question: what is the likelihood of someone reporting problems with sleeping, according to the predictors that we've put in? So we will look at this using a JASP interface, and you will need the dataset sleepLogistic.sav, and it helps to have the lab sheet from SPSS when we're looking at the write-up parts. Grab those things, open up JASP, and we will get started. So let's take a look at logistic regression in JASP. We'll need to open our file for the sleepLogistic.sav, wherever you put that. And as usual, the first thing we want to do when we open up a file is check it out, make sure that the variables came in correctly. For example, right here on ID, we know that that's a nominal, so we are going to change it from scale to nominal. And then with our research question, does a certain set of predictors indicate the likelihood of someone reporting a sleep problem? And the predictors we're interested in are the sex, age, and then we had hours of sleep per night on average, and there was trouble getting to sleep and trouble staying asleep. There you go. There's the stays asleep problems and gets to sleep problems. And our outcome is this one. What is the likelihood of someone reporting a problem with sleeping? And most of these are categorical, except for age and hours of sleep per night. So once we know that everything has the right measurement value on it as it imported into JASP, then we're going to look for descriptives. And that's part of preparing the data for analysis, and also checking our assumptions, like that variables are categorical, that our outcome is categorical, but also our preliminary, because we have both continuous and categorical predictors now. So I'll get a descriptives panel here, and I'll call this one descriptives continuous. And my continuous variables are age and hours of sleep on the weeknights. And again, right away, my results area starts filling in. I can see that the average age is 43.8.9, almost 44 years old on average, and a standard deviation of 12 to 13 years. And then hours of sleep per night on average, almost 7, with an hour, more or less, standard deviation. So with our descriptives, we have the valid, the missing, the mean, and the standard deviation, right? And the min and max. And with logistic regression, it's not as concerned with the univariate normality of the predictors, but it does care about multicollinearity. In other words, are these predictors too highly correlated? So let's go ahead and grab a panel for correlation. So I want age and hours per night of sleep, and finding out, are these two predictors, the continuous ones, correlated? Well, it looks like they are significantly correlated at -0.196. And because for multicollinearity reasons, we're only concerned with 0.9 or greater, it looks like we don't have a problem with multicollinearity here. So good there. I can go ahead and label this multi. And we are good there. Next, we want to describe the categorical variables. So getting a new panel for our categorical variables. So I'll call this one descriptives categorical. Our categorical variables, well, our outcome is categorical, and that's the problems getting asleep. And then we also had problems staying asleep and getting to sleep. So there's our outcome of reported a problem sleeping. This is reported a problem staying asleep and reported problem getting to sleep. And we had one other categorical, which was gender. So with these, it starts filling in that descriptives table, but as categorical variables, most of this we don't need. So starting with our statistics area, we can say, no, we don't need mean. We don't need standard deviation. So everything coded 0 means no. They did not report a problem sleeping, or they did not report a problem staying asleep or getting to sleep. And then 0 on sex is female, whereas 1 is male. So yeah, we know the min and max because that's exactly how the data are coded. And that means we don't really need them in that table. Here's the only information that's useful to us for categorical variables. How many are missing? But we could use some more descriptives here, and that will be down in our tables, asking for frequency tables. So here, how many reported no sleeping problem? 152, which was 56.5% of those who reported their sleeping, because we have 2 that are missing. 117 cases reported, yes, I have a problem with sleeping, and this is 43.5% of the sample who reported. Similar with problems staying asleep, no means 0 means no, they didn't have a problem. 1 means yes, they did have a problem staying asleep and getting to sleep. And then female, we have 150 females, 121 males out of those who told us their gender. So the important thing to check out here in terms of assumption check is, do we have enough sample size in each of these levels of the categorical variable? So it looks like we're ready to run the logistic regression. Let's go ahead and fold this one down, and we will go into regression, and in the classical area you're looking for logistic regression. Cool. Our dependent variable. What is the likelihood of someone reporting a problem with sleeping? That's answering our question there. And then what predictors do we think might increase or decrease the likelihood, and that's the key word there for logistic regression, is the word likelihood. What is going to increase or decrease the likelihood of someone reporting a sleeping problem? Well, our question says that we're checking out sex and some categorical variables of problems staying asleep and problems getting asleep. And these are all categorical predictors. So those are going to go into the factors field. In the covariance field is where we put the continuous predictors. So we had age and hours, average hours of sleep per weeknight. So those are all of our predictors, but we had to tell JASP which ones were continuous and which ones were categorical, which makes it really important when you read in the data to make sure these are coded correctly. So let's look at what we have in our logistic model so far. We have the H sub O model. That's called the null model because it has no predictors in it. And then the H sub 1 model is the one with predictors, or the more complex model. And what's going on here is a chi-square test saying, what is the goodness of fit here? Does having these predictors increase the goodness of fit over the null model? And that's what the chi-square is testing here. So we have our chi-square results, 76.02. We have our degrees of freedom, and we also have that it's significant, so that tells us that the model with the predictors was significantly better than a null model without predictors. That these predictors significantly tell us or contribute to predicting the likelihood of someone reporting a sleeping problem. And then here they give us a few effect sizes we can use. Normally we see Nagelkerke or Cox and Snell, so you would choose from one of those. And then we get down to our coefficients here. And for this, we want to look at the p-value to be able to tell which of these predictors significantly contribute to understanding the likelihood of someone reporting a sleeping problem. Here we see that gender is not significant. Staying asleep and getting to sleep are both significant because they're under P05. And age is not significant, but hours of sleep per night is significant. So we have a few significant predictors here to work with, but we're missing information that we need for interpreting the model. So we'll go back to our panel here and take a look. So here in our model area, we have all the predictors that we need, and none of them are added to the null model. That is fine. Let's look in statistics. So here, we want to add some information that we need about our coefficients. We need the odds ratios because that's going to tell us about what is the likelihood difference going on according to each of these predictors. We also want the confidence interval of the odds ratio. So when we turn on confidence interval, it adds the information over here, but this is not about the odds ratio. This confidence interval at first is the confidence interval around the estimate. So this is the regression coefficient estimate, but that's not what we really use to help interpret a logistic regression. Logistic regression, we need the odds ratio. And we also need the confidence interval of the odds ratio. To get that, we are going to add in this extra little checkbox saying to put the confidence interval on the odds ratio scale. And now we have the information we need. And as I mentioned in our lecture, the number that's like no change at all is 1. Like before with linear regression, it was 0. If something was estimated at 0, it was like, okay, it doesn't have any impact. Here, if something's estimated as 1, you're 1 times as likely of doing something. That's not anything. You're 1 times likely to do yourself, right? So anything that has 1 within the confidence interval is not going to be a significant predictor. See that? But let's take a look at the ones that are significant. We have staying asleep is significant, and its odds ratio is 7.274. So that's saying someone is, I'll round to the 10th place, 7.3 times more likely, because it's more than 1, to report a problem sleeping. Those who report that they have problems staying asleep are 7.3 times more likely to report problems sleeping. And let's take the next one, also a categorical predictor, getting to sleep. For those who say, yes, I have problems getting to sleep, they are 2.02 times more likely to also report having problems with sleeping in general. So that's how we read or interpret when we have a categorical predictor using our odds ratio. So it's times more likely, and because they're more than 1. So it changes a bit here with our last significant predictor here. Hours of sleep per weeknight is significant, but it's less than 1. So that means less likely to report a problem with sleeping. And because this is a continuous factor, a continuous variable, then we're saying for every 1 unit increase in hours of sleep, someone is 0.64 less likely to report a sleeping problem. And that makes sense. The more sleep I'm getting per night, the less likely I'm going to report a problem with sleeping, right? So this one is a little more challenging to talk about because it's a continuous variable. So for every 1 hour more of sleep, I'm expecting a 0.64 times less likely to report a sleeping problem. So a little bit of a tongue twister there. So what else do we need here to be able to talk to the reader about the quality of this model and its results? We've already talked about the coefficients. We've talked about that the model itself is significant and it's got an effect size. But the other thing we want to be able to tell the reader is how accurate is this model? And we can get that in our panel when in our statistics fold down area. And here in JASP, they call it a confusion matrix. Think about how confused is this regression, is this logistic regression? Let's find out. We come down to our performance diagnostics table. So here in the yes column, this is when the logistic regression predicted yes, these cases will say that they have a sleeping problem. And 71 of them did. So the observed is the actual data. So the logistic regression was right about this for 71 cases, and it was wrong about it for 28 cases when predicting, yes, this case is going to say they have a sleeping problem. Now on the no side, this is when the logistic regression predicted these cases are going to say no sleeping problem here, and it was right 110 times when the actual participant also indicated, no, I don't have a sleeping problem. Now, our logistic regression was wrong 32 times. It said they're not going to report a sleeping problem, but then the participant did. They said, yes, I have a sleeping problem. So working the math on all of that, they tell us overall percent of correct, 75.1%. That's an indicator of how accurate the logistic model was. It was accurate 75.1% of the time. So let's take a look at our write-up and see what other information we need to glean from here. In our write-up, we let the reader know what kind of test was performed and this is why we're doing it, and what the variables in the model are. So basics, test, variables, what are we doing here? And the full model was statistically significant. So this is our stats line for the chi-square. And the model was able to distinguish between respondents who reported versus those who did not report a sleep problem. Now, how accurate was the model? It was accurate 75.1% of the time. And we can build a table, would look kind of like this, where we're letting the reader know the information from the odds ratio, the confidence interval of the odds ratio, and the other estimated items like the regression coefficient and the standard error, and letting the reader know the significance levels of those predictors, and letting the reader know where the table is. Only 3 independent variables made a unique, statistically significant contribution to the model, and those are the ones they are. The strongest predictor was if someone indicated they had trouble staying asleep, that they were 7.27 more times likely to report a sleep problem. So you see a little bit of that interpretation there, letting the reader know what the odds ratio was, but then breaking it down for them. Problems getting to sleep with an odds ratio of 2.04 indicated that respondents who had difficulty getting to sleep, they said, yes, I have trouble getting to sleep. Those were 2.04 times greater to report a sleep problem. And then the weird one, the odds ratio for hours of sleep per weeknight was less than 1, which indicates for every additional hour of sleep per night, the odds were 0.64 times lower that respondents would report having a sleep problem. And that's, again, controlling for any of the other predictors in the model. So controlling for the impact of age, controlling for the impact of gender. So letting your reader know what you found out. Now here, we need to know how many respondents were actually in the model, like not just the sample size of the whole data set, but the sample size of who was in the model. Now we can get that by looking at our observed here. All we got to do is add them together. So 110 plus 28 plus 32 plus 71, 241 is the observed how many participants were in this model. And that's what we have here in reporting our chi-square results. So this is a lot, right? We have a lot going on here. It's kind of an easy model to run as far as just in one panel that we get all the information we need here, but it is a lot to take it apart and be able to interpret from your output into the write-up. So take a look over, definitely reach out to me if you have any questions, and I look forward to seeing you at the next lab.